For millennia, humanity has gazed up at the night sky in wonder. The stars, fixed and unchanging, formed familiar patterns. But some celestial objects refused to stay put. These were the planets, our wandering neighbors in the solar system. Understanding their movement, their cosmic choreography, became a central question for astronomers. This quest to decipher the dance of the planets led to groundbreaking discoveries that revolutionized our understanding of the universe. Planetary motion is not just an astronomical curiosity, it's a fundamental aspect of our existence. The Earth, our home, is a planet too. Its journey around the sun dictates our seasons, our days, and our nights. By understanding how planets move, we gain insights into the forces that govern the universe on both large and small scales. From the formation of stars and planets to the delicate balance of life on Earth, planetary motion plays a crucial role. The story of planetary motion is intricately linked with the work of Johannes Kepler, a 17th century German astronomer. Before Kepler, the prevailing model of the universe, championed by the ancient Greek astronomer Ptolemy, placed Earth at the center. Planets, it was thought, moved in perfect circles around our planet. This geocentric view held sway for over 1,400 years. However, it was Kepler, armed with meticulous observations and a touch of genius, who shattered this Earth-centric notion. His 3 laws of planetary motion, published in the early 1600s, provided a more accurate and elegant description of the planet's movements, paving the way for a new era of astronomy. Kepler's first law, often called the law of ellipses, marked a radical departure from the ancient belief in circular orbits. Through careful analysis of observational data, particularly those collected by his mentor Tycho Brahe, Kepler discovered that planets do not move in perfect circles around the sun. Instead, their paths are slightly elongated circles, known as ellipses. An ellipse is like a stretched-out circle with 2 special points inside it, called foci. Imagine drawing a circle on a piece of paper. Now, gently stretch the paper from 2 opposite sides. The circle distorts into an ellipse, and the points where you pulled the paper become the foci. Kepler's first law states that the sun sits at one of these foci for every planet in the solar system. This means that a planet's distance from the sun is not constant as it orbits. It's closest to the sun at a point called perihelion, and farthest at a point called aphelion. This seemingly subtle difference between a circle and an ellipse had profound implications for our understanding of the solar system. It shattered the ancient Greek notion of celestial perfection, where circles were considered the most harmonious and divine shapes. Kepler's discovery showed that the universe was far more complex and intriguing than previously imagined. Kepler's second law, also known as the law of equal areas, describes the speed at which a planet travels in its elliptical orbit. It states that a line connecting a planet to the sun sweeps out equal areas in equal amounts of time. This might sound complicated, but it's actually quite intuitive when visualized. Picture a planet moving in its elliptical path around the sun. As it gets closer to the sun, it speeds up, zipping past its perihelion. As it moves farther away, it slows down, taking its time to round the aphelion. Now, imagine drawing a line from the planet to the sun at different points in its orbit. Kepler's second law tells us that if we were to measure the area swept out by this line over a specific period, say a month, the area would be the same, regardless of where the planet was in its orbit. This law has important implications for understanding the conservation of angular momentum, a fundamental principle in physics. As a planet gets closer to the sun, its speed increases to compensate for the stronger gravitational pull. Conversely, as it moves farther away, its speed decreases. It's like a cosmic balancing act, ensuring that the planet's orbital energy remains constant. Kepler's third law, harmony in the heavens. Kepler's third law, often referred to as the Harmonic Law, establishes a precise mathematical relationship between a planet's orbital period, the time it takes to complete one orbit around the sun, and its average distance from the sun. This law states that the square of a planet's orbital period is proportional to the cube of its average distance from the sun. In simpler terms, this means that planets farther away from the Sun take longer to orbit it than planets closer in. Not only that, but the relationship between the orbital period and distance is precise and predictable. If you know how long it takes a planet to orbit the Sun, you can calculate its average distance from the Sun and vice versa. Kepler's third law reveals a remarkable harmony in the solar system, showing that the movements of the planets are not random, but governed by a fundamental mathematical principle. This law was a crucial step towards understanding the underlying force that dictates these movements: gravity. Kepler's legacy, a springboard for Newton. Kepler's laws of planetary motion were not merely descriptive, they were revolutionary. They provided a precise mathematical framework for understanding the movements of celestial objects, replacing the earlier, less accurate models. But perhaps even more importantly, they laid the groundwork for Isaac Newton's law of universal gravitation. Newton, born just a year after Kepler's death, inherited the legacy of Kepler's discoveries. He realized that Kepler's laws weren't isolated phenomena, but were manifestations of a universal force, gravity. Using Kepler's third law, Newton was able to derive his law of universal gravitation, which states that every object in the universe attracts every other object with a force proportional to their masses, and inversely proportional to the square of the distance between them. Kepler's laws, therefore, were not just about planets. They were about the very fabric of the universe. They demonstrated that the same force that makes an apple fall to the Earth also holds the Moon in its orbit and governs the movement of planets millions of miles away. Planetary motion today, from spacecraft to exoplanets. Kepler's laws continue to be essential tools for astronomers today. They are used to plan space missions, to understand the formation and evolution of planetary systems, and even to discover new planets beyond our own solar system. When sending a spacecraft to another planet, engineers use Kepler's laws to calculate the most fuel-efficient trajectory. By understanding the orbital mechanics of the Earth and the target planet, they can determine the optimal time to launch the spacecraft and the maneuvers needed to reach its destination. Kepler's laws are also crucial for the study of exoplanets, planets that orbit stars other than our Sun. By observing the slight wobble of a star caused by the gravitational pull of an orbiting planet, astronomers can use Kepler's laws to determine the planet's mass and orbital period. This allows them to characterize the planet and understand its potential habitability. Our place in the cosmic ballet. Understanding planetary motion is not just about deciphering the movements of distant celestial objects. It's about understanding our place in the cosmos. It reminds us that we are part of a grand cosmic ballet, where every object, from the smallest asteroid to the largest galaxy, is in constant motion, governed by the same fundamental laws of physics. As we continue to explore the universe, both within our solar system and beyond, Kepler's laws will remain essential tools for discovery. They serve as a testament to the power of human curiosity and our ability to unlock the secrets of the universe, one orbit at a time.